Hi everyone. Let's do a virtual work analysis to find the horizontal deflection of B and the vertical deflection of B using virtual work on this frame. So here we have a frame, A, B, C, D. You see the moments of inertia vary over the different elements. The information is given here. We're going to use I of 180 inches to the fourth. Area of the column and the area of the beam are given there. Now, something that's a little bit different for this problem in particular is that we're going to consider both bending and axial deformation. Right, bending and axial. Now, in class, I've mentioned that the axial deformation is very small compared to the bending deformation of beams. So this is kind of just an exercise to show that the actual difference between these two with some hard numbers, and some reasonable loading. You'll see that the axial deformations are very, very small compared to those due to the bending deformations. And I just want to show you how to lump those together, the two virtual work expressions that we've learned in class, how to lump those together. It's literally just a sum, but it's still worth showing how we do that. So back to this frame, here's point B. So we're going to look at the horizontal and the vertical deflection of this point B. So first, we have to evaluate this frame with the real loading, so that's the P system. Now I'm going to skip some steps here, but here's the frame, right? And I've posted the whole solved example as a PDF on Titanium. So you need to take a look and make sure you can fill in the gaps, because what I'm skipping is kind of the basics, the statics essentially of finding the reactions and finding all these internal forces. But this is relatively simple loading, so I hope that you can fill in the gaps just scribbling on a piece of paper while you're watching this. Hopefully you don't get stuck too much, but if you do, let me know. Okay, so here we've got this one, we've got this simple loading. If I sum moments about some point, right, I can find, if I sum moments about A, I can get this reaction. dy is 21.5, right, summing moments about here, I can find dy. And then from some forces x, some forces y, I can find that ax is 0. That's no surprise, right, because there's no applied load in the x, so there should be no reaction in the x. And ay end up with 36.5. Okay, so from here, the way that you're thinking about frames is this reaction is telling us that this column, since it's straight up and down, right, this column is transmitting the vertical load, transmitting the vertical load down to the pin, and I end up with this. And there's no y, so there's no shear in this column, which is kind of odd. It's a little bit odd, but hey, how can you have shear? There's a roller over here. There's nowhere for this thing to react in the x and give any shear in this column. There's no applied load, so there's no shear. So this column in the P system, right, since these are our real loads, this is our P system, so I'm just going to circle this and say there's no shear. And this is a pin. If there's no shear and there's no moment at one end, there's no way for there to be any moment. There's got to be 0 moment. But there is axial load, so I'm going to write normal force, right? And remember the internal forces, this is normal force. That's Fp is minus 36.5 because it's a compression, yeah? If I cut a free body of a little chunk of this, I'll find out that it's in compression, so now I have that one. Well, that column was pretty simple, right? Now let's move over to here. So I'm going to draw the bending moment diagram of BCD up above. Okay, so I cleaned this up. I have a 10 down, so it means I have negative 10 for shear. That was easy. Nothing happening here. There's no loading, so there's no slope. Negative. This is a free end. That means there's 0 moment. I have a negative slope. I go down. Negative moment. Now, for frame, this is where it becomes important to pay attention to what's going on in the frame. Now since this column was so simple, we didn't have to consider any moment or shear coming up to this joint, this rigid joint, right? So now the only internal forces that are acting on this internal joint here's C. The only forces acting on this internal joint, this is all 0. I have shear and moment here. This is negative shear. That means plus goes like this, right? Negative shear on this side means it goes up. If I transfer to the other side of the cut, it means it goes down. So I have 10. Here I have 36. Right, this comes from the AY, 36 here. That means that this one has to be up or down. Down 26.5, right? This has to be down 26.5. You can also find that out by looking at CD. Let's look at CD over here. Here's dy, it's 21.5. Here I have my distributed load. I can find out that for this thing to be in equilibrium, I have to have 26.5, and sure enough, 26.5 on this side of the cut goes up, on the other side of the cut goes down, right? Because this point is essentially joint C. Okay, so this is just a little review on the frame analysis. Now I can do the exact same thing with the moment. Here, the moment I get is negative 50, right, because it's negative 10 times 5, so I get negative 50. So negative 50 means if this is positive on the beam side, I flip it, I have negative 50 on this side. Now this one's 0. For the joint to have equilibrium means this must be negative 50. On the other side of the cut must also be negative 50. So on this beam, CD, I expect to see negative 50 right here as well. Well, that makes sense because this is kind of like a continuous beam. So it should be negative 50. And then, what's my shear? Well, I didn't do that part yet. Well, yeah, I did. Look, it's 26.5. So I go up. I kind of crowded my shear diagram out here. Let me bump it down a little bit. Let's just make this line the 0 line. There's negative 10. And then I had the reaction 36.5 up, so I'm at 26.5. And now I have the distributed load, so I go down. I end up at 21.5. If you can do that math, right, the area under this curve gives you the difference between those. You can find this point if you'd like. You don't really need to at this point, but that's okay. So now I have this one, that's my shear. So that tells me something about the moment. I just confirmed that it starts at negative 50, so I'm going to start at negative 50. I have a positive slope. Here I have 0 slope. And you can do the calculation here to see how much does it change from negative 50 up to where does it go. Maybe it doesn't go all the way up to positive, but I already did the math, so I already knew that. But you can check yourself, right? So positive slope, I end at 0 slope, means I must go like this. This is now 0 slope down to negative slope, and I have to end at 0 because this is a roller. So I have some shape like that. Okay, so that was kind of just the frame analysis part, right? Good. And this is our P system. So this member, we're not even going to worry about it because no matter what it is, in either of our Q systems, this is going to be 0.
What I mean is that MP is 0. We still have an FP.
Now for BC and CD, I have a function. So let me clean this part up. So the board's clean. Let's go ahead and write moment functions, MP of x for BC and MP of x of CD, these two segments here. This is just a straight line, so that's a pretty simple one. Let's write it down. The slope is negative 10. All right, slope is negative 10, so I have negative 10 x and there's no y-intercept if I start x this way, right? There's no y-intercept there, so I have negative 10x, done. Now this segment is curved, so I'm going to have some kind of an x squared here, but let's go ahead and cut a segment of this beam so that I can write the equation. So if I start at C, this is point C, this is kind of a reaction, right? Comes from this axial force and then was reduced by 10. If you remember, I drew the joint equilibrium here, but also you can just look at the shear. The shear tells you the internal force here, right? This is point C. This is 26.5. That's the internal shear right at point C. And then the internal moment was, I'll do the correct thing there, minus 50, like that. Okay, so I'm going to cut a distance x, so I'm just cutting somewhere in here, right, from C to x. So I need to replace, or I need to copy over my distributed load. This is 2.4 kips per foot. And then I'm looking for the internal moment, so I'm making a cut right there. So the internal moment is mp of x. So this is the information that you need. I'm going to give you the equation. You can find it by summing the moments, right? So this is minus 1.2 x squared plus 26.5 x, then minus 50. So I have that one, and I have that one. Okay, these are my two MPs that I'm going to use for both of the Q systems, horizontal deflection at B and vertical deflection at B. So let's go ahead and just quickly write down those two Q systems. This is for delta B horizontal. This is for delta B vertical. So I have one kip there. I have one kip like this. Right, so let's do the horizontal first. Again, I'm going to make you do the basic statics. I don't have time to go over the whole thing. But using these lengths, right, you can get these reactions, and then you'll find that the moment, here maybe it's easier if I draw the moment like this, huh? Here's the moment. This one also has moment like that. This is 12. This one is minus 12. Okay. Then for B vertical, so for B vertical I have one kip here. This acts like a cantilever, so that one's easy to do. This is negative 5. And then the reactions are 5/4. This is 0, right? There's no applied load in the x, so how can there be any reaction? And then this one is down 1/4. So this corresponds to a positive shear, so it makes sense that we have a positive slope moment. And sure enough, we have negative 5 there on both. Now, what I didn't do here yet was the axial. Now this segment right here, of course, has some axial load, so FQ is negative 1. Over here there's no axial load, and then there's some axial load in this column, right? Looks like 0.6 in tension, so this should be FQ, oh sorry, in tension, so positive 0.6. Good. These moment equations are pretty easy to write. So let's say for AB, right, that's this one, AB, we have MQ X going from, actually, do I care? Do I care if there's any moment right here? No, because it's going to be MQ times MP, and there's no MP, so let's not bother doing that one. Save ourselves some work. But here I have MQ, and here I have MP, so I better write the equation for this one. So for this one, I have, if I start x this way, what can I write? The y-intercept is 12. The slope is negative 0.6, so I have negative 0.6x. That's MQ for CD, right? CD. Good. Seems like all I need, just this and that. And then how about for this one? This one is easy, but now make a little note here. I'm not going to use m of x. Not used. Watch. We'll use the tables to do that one, just to show you how to use them. Okay, here I can say MQ. Now here I can't really rely on the tables because I got some weird shape here, but here I can use the table because I have triangle and triangle, so that one's easy to do. This one, the slope is positive 1/4, so 1/4 x, and the y-intercept is -5. So there's that one. Okay, so I encourage you to write these down because I'm going to erase everything now that we have the P system and the two Q systems. Write all these equations down and we're going to copy them over and do the virtual work calculation. Let's write out the virtual work expression for the beam that includes both bending and axial terms. Right? So I have BC, that's that little diving board part. I have CD, that's the long beam, and then the column AB. So each element has both a bending and an axial term. So for the BC, if you remember, the MQ was 0. MQ was 0 for the horizontal, deflection, right? The Q system in the horizontal this way. And then the axial, it was, the FQ was non-zero, but the FP was 0. So this one, it was 0. How about for the long beam? MQ was not 0, MP was not 0. Oh, and notice, I have 2 EI here because it was 2I. Same over here, I had 2 EI. Then, so these are both non-zero, so I'm going to keep those. Then, both FQ and FP were both 0. There was no axial load in that. That makes sense, it has a roller on the end, so how could it have axial load? Okay, and then for the column AB, MP was 0. In the P system, there was no moment. But there was, in both the FP and the FQ system, both had axial load, so we're going to keep that term. So essentially, we end up with this term and this term we're going to carry through. So let's do that. So I plugged these in. This is for the long beam part. Remember, we have MQ, this equation, MP is this equation, and then I carry through my 1/2EI dx, and then this axial term comes from AB, but it's fine, right? This external work, even though it causes both axial deformations and bending deformations, I don't have to do anything special other than just sum up the internal strain energy. So that's kind of the one interesting point or interesting part of using virtual work, is that as long as you express the external work and the internal strain energy, they're equal. Doesn't matter if it's bending or axial. Okay, anyway, so we just sum them up. So here's the bending term, here's the axial term for the column, this is for the beam. Now I just evaluate and sum it up, and I did that on the page, right, on the PDF, so I'm not going to go through it here. I end up with, that's a delta, BH is 2800 over EI, and then that axial term is minus, right, because I have plus and minus, so minus 0.018. I end up with, if I plug these in, right, multiply by 1728, and then divide by E and I, end up with delta BH is 0.90 inch, and that's positive, right? We got a positive number, means goes to the right, just like our Q. Okay, so that's the horizontal. Let's do the vertical one. Okay, so let's write out the vertical terms, but I'm going to skip some of the steps here. I want you to do the exact same thing that I just did for the horizontal. Write out every term for every segment, and then cross off the ones that are 0, just so that you really see where do these terms come from that I'm going to write here. So I'm going to put the first one here, and I'm going to tell you it's the bending term for segment BC. So the bending term for segment BC uses the MQ, and the MP. But if I take a look at those two diagrams, I see they're both triangles, right? And they're both over this 5-foot length. So I have this nice simple shape. I can use the table of product integrals and just plug in these values. This will be M3, and this will be M1. This integral, 0 to L, which L is going to be 5 in this case, of MQ, MP, dx, is going to be equal to 1/3 M1, M3 times L. And you'll see this term in the table. So let's plug these in, and we'll just write it right here. That's the product of this integral. Now I need to add in my 1/2EI here, so don't forget that. 1/2EI times this term, 1/3, M1, right? M1 is the Q system, so it's -5. And then M3 is the -50, that's the P system. Length is 5. So straight away, I have my integral, the result of that integral, so it's nice. That makes it nice. Okay, so I'm going to get rid of this because we don't need this now. I just wanted to show you where that came from. So we had that bending term for BC. We end up with, and I'm going to write it down here so I have enough room, the bending term for the long beam part, so integral 0 to 20. Now I can't use the tables for that one because it had that sort of compound. There was too much of a function there. It wasn't a simple shape. So I end up with 1/4 x minus 5. That was the MQ system. Minus 1.2 x squared plus 26.5 x minus 50. 1/2EI dx. And then I also had an axial term for the column, which was -5/4. And that's the FQ, -36.5. And then, oh, sorry, A was 6. And then E. Okay, so I have bending term for BC, I have bending term for CD, and then this is the axial term for the column AB. So I'm going to evaluate all that, and again, I showed it in the on the PDF. So just to show, the answer is BB 279. Now this comes out to be negative. This term comes out to be negative. This term alone is negative 1166.7 over EI, and that's the vast majority of the deflection. This one is pretty small, but this axial term is super, super small. This axial term is about half of this one, and this one's already small, and both of them combined are much less than this term. So just look at the PDF and you'll see the relative values of those two. Okay, so I got a negative. That means it goes which direction? I push down with Q, so that means it goes up, right? So negative means up in this case, because my Q was down. My Q was down. Therefore, delta is up. The toughest part for you is probably going to be weeding through the frame analysis, so just brush up on that. Just remember that for frame analysis, when you have a rigid joint, that joint has to be in moment equilibrium, and has to have equilibrium in the Y and the X, and that'll help, I think, help you get through that one. Okay, thanks a lot.